Okay, so I guess I'll start things off. So I just want to welcome the university students who are attending. It's the first time we've done sort of a webinar focused on the SAE type competitions and sort of how HyperWorks has been used for them, just to introduce you guys to our products. My name is Greg Delbridge. I'm a senior application engineer here with Altair Canada. Altair Canada is one of 44 Altair offices worldwide, and we've got 2 in Canada, one in Toronto in the GTA area, and the others in Montreal. Altair HyperWorks software, hopefully you guys are familiar with it. It's used by engineers in nearly 80 companies and by engineering students at more than 20 universities here in Canada. Hopefully, HyperMesh and HyperView are kind of the marquee modeling and visualization software solutions for finite element analysis. They're the market leaders in automotive, rail, commercial vehicle, consumer products, and they're also the fastest growing solutions in the aerospace industries worldwide. So just today, my colleagues from Altair Germany and Altair India are going to talk to us about how HyperWorks is being used by SAE teams worldwide and introduce Solid Thinking Inspire. Inspire is a new Altair solution that is helping designers and design engineers to create the most structurally efficient and lightweight designs possible, just right from the outset of the design process. Solid Thinking Inspire, it's the perfect solution for motorsport teams who need, component designs sort of tailored for 3D printing and additive manufacturing, as well as one-off designs. So at this point, I'd just like to, and I guess at the end we'll go over what Altair Canada does for the SAE teams and universities, and what we want you guys. We want you guys to succeed, and we want you guys to succeed with our products. And after that, we'll open it up for some questions. So at this point, I'll turn it over to my colleague Matthias from Altair Germany, and he'll take us through the CAE-driven design process.
Okay, thank you, Greg. This is Matthias Gölge from the German office. Welcome. I'm really glad that you're attending this webinar. It's a kind of novel thing for us in this way. Currently in Germany, actually today and tomorrow, we are hosting a Formula Student event workshop for about 100 students. So there's quite some traffic, quite some interest in our office, which is really inspiring. And actually, this was also a kind, let's say, of motivation to introduce you to our concept, the CAE-driven design process, through this kind of webinar. And maybe this is just the first webinar of a series of webinars we are going to offer you. Actually, it depends a little bit on your feedback at the end. So what I'd like to start with is a quote given by Henry Ford. Coming together is a beginning. Keeping together is progress, and working together is success. In fact, I really like this quote because it reflects our, let's say, working philosophy. For us, it's important that we not just get started together to do something together. It's more about our common future. So we are really aiming, and we are really looking forward to working together with you in the future. And there are a lot of, let's say, opportunities, certainly a lot of challenges on your way or in the design process, and we want to be, let's say, your partner. Of course, we are more than happy to sponsor your activities, but we want to be your partner as well. Just some kind of case studies, let's say, of appetizer at the beginning. Why are so many Formula Student teams around the globe let's say, making use of our sponsoring package? This is a case study provided by the University of Stuttgart. I'm not sure whether you know those guys. They are quite successful. Down here you can see the challenge. It's remove weight and improve performance of the vehicle. And in fact, this is the first common starting point. Most of the teams we are talking to, they face certain weight issues, and we're going to show you later on in this webinar solutions how you can not only, let's say, fasten up your design process, but deliver at the very end a product which is more innovative and with, let's say, which uses less material. So essentially we talk about topology optimization. There's another case study that's actually from a global solar team from the University of Michigan. I guess you're familiar with this team. It's also about using optimization our finite element solver is called a named object to minimize the weight of the composite structures. That's also another topic which is, of course, very, very important. Just thinking about the monocoque structures which are widely used in Formula Student race cars. So to give you an idea, I'd like to challenge you a little bit with this little, let's say, design project. It's rather simple, but it's very illustrative about the things we're going to show you later on. And by the way, this is not a marketing webinar. We are really going to talk about technique and technology in here. So just think about this little challenge over here. The yellow area is what we call the design space. That's the area where you can change the geometry. The task is to determine a solution which uses as less material as possible. At the tip over here, I hope you can see my pointer. There's a force applied in the vertical direction with the with the same magnitude upwards and downwards. You can apply certain constraints over here if you want to. And now think about how can you design this geometry in such a way that only a minimum of mass is used, as I mentioned before, but at the same time the design must fulfill certain criteria such as the opening of the clip over here in the vertical direction shouldn't exceed a certain threshold. So what typically happens is that the students we are running this exercise with, they start chopping off the component or the area, for instance. They trim off a certain part of the geometry of the surface over here, or they start drilling holes in here. Somehow it helps them to reduce weight. Sometimes they realize that by changing the geometry, they don't meet the target displacements, meaning they are, let's say, quite far off from a kind of optimal design. And it turns out to be an iterative process. And this process is sketched, just a second, is sketched in here. So if you think about your design process, you typically start with a CAD solution at the beginning, or a CAD geometry. You take the geometry into your finite element suite or your finite element preprocessor. You build a finite element model, you apply the loads, the material, and everything what is needed to run the finite element analysis as such. And then you look at the results, and over here, verification, you then realize that your CAD geometry, the thing you started with at the very beginning, fulfills your needs or not. If the results over here tell you no, displacements, for instance, are much too high, you need to go back and you have to restart over here, changing the CAD geometry. Most of the time, the overall shape of the geometry remains pretty much the same, but you tweak around a little bit over here and over there, and then actually hoping that the next iterative process over here is more successful. The problem is simply that you need to question yourself, how efficient is this approach at all? You don't know how many loops you need. Maybe if you're extremely lucky, you just need one run and you are done. But then the question still remains, can we do it any better? I mean, how good is your solution over here? Is your competitor, meaning the other team, maybe doing better, is ending up with a more innovative solution? And there are, of course, part of this process, a lot of uncertainties. How long will it take you really to get from here till the very end, to end with a product which you're going to use in your race car at the end? And again, what about the quality and the performance of the component? Even though this is already, let's say, simulation driven in here, there are a lot of uncertainties. And I know that you guys are always short in time. So in Germany, most of the racing teams, they claim, or at least they try to have design freeze end of December, let's say mid-January. They head towards, let's say, manufacturing in around, let's say, March, April time frame. And some teams manage to have their rollout end of May. So that's the kind, let's say, of time schedule they have here in Germany, because the German Formula Student event, the race, the competition, takes place in the first week of August. And it's, of course, at the very end, once the car is built, all about testing, really driving, making as many miles as possible. So the time is really limited. And again, this comes back to the question, is this design process here really efficient at all? And what we propose, not only to the Formula Student teams, but also to our commercial customers, of course, is this concept. We, in fact, promote to put CAE upfront of the entire process over here. And you can look at the same, let's say, sketch in a different way. Typically, the CAE engineer gets the geometry from the designer, applies the loads, and checks over here, verification, whether the geometry sustains the loads or not. If you follow this upfront optimization, conceptual optimization process, the story looks a little bit different. Here, we ask the designer, give us the loads, and we provide you with a geometry which will sustain the loads. So it's a different, let's say, way of looking at the design process. And what's happening over here is, in fact, concept optimization. Concept optimization delivers you some ideas how the geometry may look like. Most of the time, concept optimization delivers designs you don't think of because they really look very, very different than, let's say, human inspiration as such. And then from here, from the concept optimization input, you go into the CAD system, you make a kind of first interpretation of the concept design, and you go through this process. And typically, the story ends by shortening the entire design cycle and reducing weight. As a kind of average number, most of the teams report weight savings in the order of 20%. Of course, it always depends how good the starting geometry, their old geometry was. But roughly 20%, sometimes 20% plus is the result. So this is the geometry we started with. And if you look now at the concept design solution, would look like this, for instance. What you can see over here is actually the geometry which was reinterpreted by students, and they put the whole thing into the finite element program, which is called OptiStruct. Of course, at the same time, you can claim in here certain modeling mistakes, but this leads us to a different story. For instance, here, the kind of meshing most likely is not really appropriated, just one element over the thickness. But this is, as I mentioned, a different story. The point simply is that starting with the yellow design area, ending over here with this geometry, which is really, let's say, lightweight, is something which typically takes one iteration, and you are almost done. So that's a pretty, let's say, efficient approach. And this again illustrates the same process again. You start with a rather, let's say, sketchy or bulky component or structure over here. You don't think about the details a lot at that point, because the details will be introduced by the optimization algorithm later on. That's what I mentioned with the kind of bulky design space. You apply your loads, the materials, etc., and you go through this process from here over here. You may apply what is called shape controls. Shape controls simply means you want to have certain symmetries in your final design. The optimization tool then pops out with this kind of concept design, which still needs certain refinement and interpretation, because sometimes the ribs, the thickness of the ribs are, let's say, not continuous. Sometimes they get a little bit thinner, they taper out. Sometimes you don't like this kind of geometry. So there's still some open area for you to improve the geometry. But again, this way from here, from the first slide down over here, is typically something which is done within a few iterations. much faster than the, let's say, traditional CAE process. And in fact, this slide brings me to Manuel Ramsaier. Manuel Ramsaier, I go back to our agenda. He is a former Formula student member here in Germany, and Manuel Ramsaier is now going to present you some of the work he did in the past. So, Manuel, I'm now making you presenter.
All right, I hope everyone can hear me.
Yeah.
And I hope everyone can see me now. Or at least my screen.
Not yet. Not yet.
Not yet?
No. Okay, now I see a screen.
Now, okay. So I'm happy to present you hands-on experience because I was a member, or I am still a member of the Formula student team, and I did go the process with Altair together, and I can share those experience with you, which might be of worth for you. So first of all, who is this guy talking to you? I'm born 30th of July 1989, and I graduated recently in August, got my master's degree, and I'm now working at the university as a doctoral candidate. And my first contact with Altair was at a practical semester which I had done at Liebherr Aerospace, and at that point I did not know anything about the finite element method, and it was rather hard for me to go just from the start to evaluate the software for the company. But within 6 months I learned a lot about it, and Altair was helping me also a lot with it. Okay, what I'm going to tell you. First of all, how we managed to optimize our gear wheel design. In the past few months we optimized only one part with OptiStruct at our car, and this was the gear wheel. And it was rather a fun project, but I will come to that later. And I also will give you recommendations for your studying and how you get the most of Altair's offerings, and also some recommendations on how to simulate in the Formula Student team or on the Formula Student car, which Matthias also told you earlier. And the rollout video, I will paste a link in the description because I don't think it will run very well if I upload it because my internet connection is not that good. Okay, now let's start with the first topic, the gear wheel. On the right side you can see our original design, and it has never been calculated in the meaning of simulation with finite element methods, because at our university the students in the third or the fourth semester, they really don't know anything about the finite element method, and so they didn't calculate it properly. It has never failed though, so it was kept as a reasonable design. And one day, therefore it's called a fun demo, one day I walked over to a colleague of mine which was responsible for this part, and I just wanted to show him the HyperWorks capabilities because I thought it would be an easy part. And it turned into that we really manufactured the part almost exactly as OptiStruct told us to. And after all, we got a 20% weight advantage. It looked better, it also not failed, and it was calculated. Much experience granted through this project. It looked better. Now I have to show you. This is the optimization on the left side, what you get out from OptiStruct. It's the density of the elements, and you have somehow interpret it, and most importantly, you have to validate it. So we optimize the part, got the left picture, and transferred it into a CAD model, and rechecked whether the stresses are in the reasonable limits for us. And that's the picture on the right. Now our car, you can see here without the wing rods, but I think you can imagine that. And it was a really cool car. It, I think, had most of top 10 winnings, and we almost did a top 3 in the racing in Italy. Let's move on to the recommendations for studying. The support forum, which will be discussed later, is of great help. It is professional help for free, and I really can recommend it for you to, if you have questions or if you have a problem, go there, post your question, and you will get help rather fast. I experienced it 24 hours at maximum. And also I would recommend to you that you start to learn how to do simulations, if you're not also doing that to this point, because it's a highly wanted qualification later in the industry. And another point is that you never ever trust your simulation blindly. Always double check, always make sure that the simulation is within reasonable limits. And for that point, the Altair ebooks are help for beginners, as it describes the theory behind the finite element method very easily and straightforward. Now this slide, I think that's the most important slide, as it covers almost everything you have to know for to do the optimization parts for Formula Student. Racing means getting somewhere fast. Okay, that's plausible. And a mass reduction helps directly. As you know, F equals m times a. If I have the same force, less mass, I can invest this energy in the acceleration. But less mass doesn't help only. Only less mass. Just imagine a race car built out of pure magnesium. It will break. So you have to increase your stiffness too. And for increasing the stiffness, you have to minimize the compliance. And that's the goal you have in your OptiStruct setup. Minimize your compliance for maximizing your stiffness. The first thing you want to look at in Formula Student: how do you get the most of the mass? You just want to invest mass on that locations where it is needed, where it is stressed. So in your optimization scenario, what's fixed is you want the maximum stiffness and minimize the compliance, and you give volume frac. What's this volume frac? Volume fraction means that you say, for example, 30%. That's the maximum value the solver gets material regarding the original material for the optimization process. So the parameters you can experiment with is maybe the volume frac. Give the solver 10%, 20%, 40%, 30%. Experiment with the minimum and maximum member size, with the constraints and others. If you invest in simulation knowledge and in Altair HyperWorks products, you will get to know those terms very shortly. As a small example, I want to present you the 3-point bending beam. It's really rather straightforward. You have two bearings, an enforced displacement, and a bending moment. First, you have to model it. So you have to decide whether you model it in 2 dimensions or 3 dimensions. You have to do the bearings. You have to give the load case. And then you're going to analyze it. In the analyzation, you have the stresses, the displacements, and first check if your boundary conditions are set reasonable. When this is okay, you optimize it. And with that optimization, you get those structures we talked about earlier. From that, you go back to CAD and reanalyze it. That was in very short terms the thing you got to do if you want to be the fastest car on the race circuit. So for that, I want to thank you for your attending. and I picked a rather a little bit different quote. If everything seems under control, you're not going fast enough. So I want you to get your best out there, invest in those Altair products, and really get the best parts possible, and we see us on the race circuit.
Okay.
If you have anything, questions, I will paste my email address in the chat, and you can contact me or the support from it at any time. Thank you.
Thank you, Manuel. I'm making myself presenter again, just for a minute. Show my screen. Oh, you can see my screen again. So thanks again, Manuel. Dear attendees, I hope you're not scared off by the terminologies with the compliance, with volume frac, load cases, etc., etc. As Manuel mentioned, we are ready to help you. So there is a kind, let's say, of transition phase where you can start really from scratch, being or becoming a kind of expert in a rather, let's say, short period of time. The good thing is, in fact, that the Altair software suite offers, let's say, different levels of how is it called? Different levels of complexity, so to speak. There is, let's say, the high-end level, which I would, let's say, address the composite optimization. So if you think about the layer setup, layer orientation, fiber orientation, layer thickness, things like this. And at the, let's say, lower end, but still talking about optimization, we offer you a tool which is called Inspire, Solid Thinking Inspire. And in the next part, in the next section, Rahul from India, he's going to give you a live demo, not PowerPoint, really live demo about how to use Inspire, how to get started. And I'm sure once you are familiar with Inspire, the next steps, making the advantage or making use of the more advanced optimization technologies which are available along with other products. So if you talk about, for instance, size optimization or shape optimization, composite optimizations, those steps, they are not too difficult. I mean, it's still engineering, and you know the old saying, garbage in, garbage out. So you need to know what you're doing, but it's a kind of gradual step of getting to know how the simulation stuff works. And now, Rahul, I make you presenter.
Yeah.
Okay. And yeah, we are now interested in your story.
Thanks, Matthias. Just a little bit of PPT before the live demo. I think right now we're just going to focus on one particular tool in Altair. It's probably the tool we are most excited about, and which we think students like you would be most interested in, and which you can get the most out of. So Inspire enables design engineers like you to create structurally efficient concepts quickly and easily. So when we say structurally efficient, we mean very strong, and still it weighs very less. And so the traditional design process will be to check if your design will support the required loads. But Inspire enhances this process. You give your loads as input, and then Inspire comes up with a design which is of low weight, but is still stiff enough to do what it's required to do. And I think we went over this quite a bit. So the traditional process is you design, you build, and you validate. And this is a very expensive process, because if you have to redesign, your initial design goes waste. And if you look at the design process we are suggesting, so you start with a design, an initial design, and then Inspire, the software, will come up with a low weight but still strong structure, and then you can redesign. So just to give you a quick idea of the design process. So with Inspire, so here is a fan, and what you do is you apply the loads that the fan will experience in service, and you constrain the regions where the fan will be bolted. And then you choose the areas of the fan where which you think can be redesigned and the mass can be reduced. And you just give such input to Inspire, and then Inspire will calculate and give you an idea of how the load is transferred within your design space, so that you can then redesign that particular component to just have the essential essential material within it, so that you end up with a low weight design like this. So I think I'll just go ahead and show you the tool right now. So this is what solid thinking Inspire looks like, and so as you know, initially we all start with geometry, or the tool has to know what your component looks like and its dimensions, etc. So there are Inspire allows you to do this in every way. So you could create your CAD geometry in your CAD tool and import it into Inspire, and also you can create your geometry within Inspire. So I'm just going to start by just giving you a quick idea of how easy it is to create the geometry within Inspire. So we have these sketch tools here. So I just click on a sketch option such as polyline here, and you immediately get a sketch plane, and you can just go ahead and sketch your geometry if you know what the cross section will look like, for example. And so it's that easy to create your 2D geometry, and you can immediately push or pull it, and you then have your solid geometry. So Inspire works only with solid geometry, and then it's quite easy to modify your geometry. For instance, if I need to put a hole in a region, so I just do it that way, and I can just modify it in any way I want, like this. So this is just to give you an idea that it is very easy to create your the geometry of your component within Inspire. But like I said, you can also import geometry from any CAD format. So it supports every available CAD format, and I'm sure you recognize some of these formats here. And in this case, I'm just saved it in the STMod format. This is the Inspire format. And just to give you a quick idea of how you can edit your geometry if you bring it in from CAD and do not actually create it within Inspire. So some of the problems with imported CAD geometry can be easily addressed with Inspire. So you can just, for instance, I have surfaces missing, and I want to fix the surfaces so that this actually becomes a solid geometry. So I just go to the problem region that way, and I can fix it by just a left click. So Inspire will identify any of these problem places, and you can easily fix it up. And you have several several options to modify your imported geometry. You can find all the holes or any empty spaces in your geometry and quickly fix it. So, and you can see that in this way you are actually creating different components, but you can also just fix your holes in your geometry with as a part of the original component, and several other defeaturing methods like removing your fillets and so on. So this is just a quick maybe introduction into the several features. For instance, I can cut up my model like this and move it around. Just to give you an idea that it's very easy to modify your CAD geometry. So I would now move on to actual designing. So so let's say your geometry is now ready. So what you do with Inspire is you initially you need to identify the region for Inspire that you think should be redesigned and where you need the mask to be reduced, for example. So you just right click on that particular part and you call it the design space. And you leave the rest as non-design space because this is the region where you would be applying your loads and constraints. So this, as you can see, is a brake pedal, and this would be experiencing a load of about 500 newtons, let's say, and you can then constrain your part like this, and you're basically saying the part is held here and it doesn't move. So what you do now is you can then enter your optimization parameters. So you can say I want to retain 50% of the mass of this component, and Inspire can remove half of the material away while it is maximizing stiffness. And you have several other options which you might need when you're designing. For instance, if you want to take gravity loads into consideration, or if you want to impose frequency constraints, for example. But I'm just going to skip those, and I'm just going to run this optimization analysis, and all I wanted to do is remove 50% of the mass, or close to 50% of the mass, while keeping it still strong enough to do its job. So as you can see, I just clicked run, and hopefully we should have our results within a minute. If you're curious, you can just find out how far the optimization run has gone already. So once Inspire has calculated its result, it's basically telling us that we can remove mass in these areas, and therefore we have a lighter design which still does the job it's supposed to do. What we would always like to do once we have a redesign component is to check if this new design will actually perform as expected, and that's possible with Inspire. So I just click Analyze here, and then Inspire will basically do a linear static analysis, and this will then tell us if the design is going to perform as expected. So since this is a linear static analysis, you can look at results like displacement and one measure stress. So I'm just going to check the results of the linear static analysis. So this tells us where the max displacement is, and if it is acceptable, and if it was better than the original design. Incidentally, you could run the analysis on your original design as well. So it's not just on the optimized shape that you can actually run the linear static analysis and view the results. So you could also animate your results and just everything necessary to post-process your analysis. So the other thing we would like to do once we have redesigned our component and we want to now maybe go to a CAD tool to actually redraw the component. Maybe for a maybe you want to make it aesthetically better or manufacturable or any other considerations that despite the structural considerations. So at this point you can ask Inspire to create a geometry out of the optimized shape. So what we call this is called smoothing, and so we basically create a smooth geometry over the optimized shape suggested by Inspire. So what we're looking at now is actually geometry, and you can then save this geometry in any format you wish, so that you can actually take it into your CAD tool and redesign it. These are the formats available to save it. And I think these general formats will allow you to take your low weight, high performing design into your CAD tool. So, so that is actually a very quick introduction into how you can use Inspire to redesign the parts of your car to actually reduce mass. But you might have other considerations such as manufacturability, and you can use certain other features of Inspire. So if we go to the original design, so just before you run your optimization, you can ask Inspire for a design that would be symmetric along a certain plane. So this would probably make it more easily manufacturable, and also depending on your manufacturing process. So if your manufacturing process is, for example, extrusion, you would then need a constant cross section all through your design. So Inspire will then give you a design shape that will have constant cross section throughout, and so there are several features like this. We're not going in detail into all of them, but you definitely have everything you need to create a part with lower weight and still performs well. So maybe finally, I just want to quickly show you that you can see the mass of your optimized part and compare it with your initial design, and you would actually see that there is some reduction in mass. And also, just another quick tip about maybe if you're learning Inspire by yourself. So I just click on F1 and on a particular feature, and then the help will take you to that page, and you could then learn about that particular feature of Inspire. So that's a quick introduction into what Inspire can do for you. So I'll just hand it over to Matthias.
Okay.
Yeah.
Thank you, Rahul. Nice presentation. Just a few comments from my side. You missed to talk about the material properties. Maybe you can simply add a few comments on it.
Yeah. Yeah. Thanks. Yeah. So of course, you have a material library in Inspire that you can use for your components. Just a second. So you can just right click on your component. Okay, so maybe I'll just skip the assigning part. So so you would want to assign a particular material to the component. So Inspire allows you to create your own materials apart from having a material library. So you can choose any material within the material library, or enter your own material values for a material that's not within the material library. Yeah. So Matthias?
Yeah, I think that's really important to know, and also you can change the units which are being used inside Inspire. So if you don't like kilogram or newtons too much, there's also an option to change the settings accordingly. I think what's very important, because some of you may have wondered that certain areas of the brake pedal looked rather, let's say, rather thin and not really, let's say, smooth or nice. Very important in the optimization process is to play around with the shape controls, with the manufacturing controls. As Rahul just pointed out, you can define the extrusion directions, you can define how thick those kind of ribs or members should be at the very end, and really by changing the draw direction or playing around, modifying the draw directions, extrusion, etc., you certainly will end up with different shapes, with different design solutions. So it's still an iterative process, but you get to the results much faster. And this brings me at that point to how to get started, how to learn something about Inspire. And I make myself presenter again, and I'm show my screen, and I'm jumping in here into my presentation, and now it's about learning. So I'm not sure whether you know about it, but the Altair University team is hosting a dedicated website that's really named altairuniversity.com, where you typically find a lot of information, helpful information about our software, about our ebooks, about the support forum, about the training center, and much more, and many other things. So to stay, let's say, informed and up to date what's happening at Altair, what kind of events are hosted, really we recommend go to Altair University frequently. We are adding a lot of posts throughout, actually every week. I think we end up adding something like between 5 and 10 posts, depending a little bit what's happening inside Altair. So this is kind of, let's say, a first contact place over here. However, when it comes to learning, again, as Rahul mentioned at the beginning, make use, or as Manuel mentioned at the beginning, please make use of our free ebooks and the support forum. But what I want to show you next is our dedicated academic training center. In the academic training center, you will find certain tutorials, tutorials which are a little bit different than, let's say, the standard training material, tutorials which are partly written by students, by customers of us, partly written by the Altair University team about different topics. For instance, you will find at least 2 rather lengthy tutorials about monocoque optimization or optimization of a monocoque. One tutorial, I think, is about 40 pages, is written in English language, and it's really explaining the entire process. The other one is written actually in French language, and those kind of materials are written by former Formula Student team members. So the Academic Training Center is really, let's say, a page you should go to view our e-learning material and additional tutorials. The other thing, as Manuel mentioned before, our study guides. The study guide about practical aspects of finite element simulation is not really dealing with the mathematics behind, so it's not really the theory. I think the libraries are filled up with books about finite element method. This is more about the practical aspects. How should you mesh your component? What are the effects of mesh density, mesh type on your results? Things like this are discussed in this study guide. There is another study guide available also for free, which is named Practical Aspects of Structural Optimization. And this one, again, is about how to set up your model, what are the definitions, the terminology you should know. And a professor of us here in Germany, Axel Schumacher, I'm not sure whether you know him, but he's very, very famous in Germany. He donated, so to speak, a chapter about the theory of optimization. It's all written in English, and it's all part of this little study guide in here, and it really should help you to get started. Of course, there's also a documentation about how to get started with Inspire. The other thing, again, very important, is our support forum. It's a moderated support forum, and we do have 2. We are going to add a 3rd member who is working on the support forum. We request our users to post issues or inquiries in English language, and there's quite a lot of traffic actually. You can get to the support forum by visiting Altair University, and then from there you are redirected to the forum. Very important at that point. Sponsoring, and I think at that point, Greg, I leave the stage to you.
Unmuted.
Okay,
am I back yet?
Okay, I can hear you now, Greg.
Yes. I had the little green microphone had left me, was letting me down, even though I said I was muted. Okay. So just in addition, for the Canadian teams of Formula FSAE, in addition to Altair University, which is a great website, has tons of material. Even though I'm supposedly an application specialist, I still go there and I learn stuff. So it is really something you guys should check out. But in addition to that, at least in Altair Canada anyway, we really want you guys to succeed. We want to meet you guys. So we open up all of our corporate trainings to you guys as well. The trainings are all free. They take place in either all or our Toronto offices. We do HyperMesh, HyperView, once a month. We do OptiStruct optimization for metallics probably twice a year, composites a couple of times as well as Inspire. Inspire, as you probably saw from the demos, is really easy. You can pick it up on your own. So the trainings are available to you guys. You're welcome to come meet us and attend the trainings, the same ones that our commercial customers have. And in addition, I don't think they mentioned this, but at altairuniversity.com you can download the student version of HyperWorks, which has Inspire, which has the full version of OptiStruct as well as HyperMesh and HyperView. And if there are pieces of that missing for the Formula SAE teams or all SAE competition teams, Altair Canada won't, if you want it, we'll also provide you a commercial license of the full-blown version of HyperWorks as well, so you have access to that if you want it. So we're really looking for you, looking to help you guys succeed, to win, bring glory to Canada. So anything we can do to help out is we're we're looking for that. So feel free to contact us. And like I said, Altair HyperWorks .ca is the Canadian version of the website, so that's where our trainings are listed, contact information. So yeah, so with that, I guess we'll open up for questions. That's pretty much all I had. I just wanted to thank everyone for putting this together for us. So with that, should we move on to questions, Matthias?
Yeah. I think it's really time to ask our attendees about, let's say, their needs, their kind of interests, because we just talked about optimization, but through HyperWorks, through our simulation software suite, you can of course address totally different topics as well, like vehicle dynamics. So if you're interested in multi-body simulation, if you're interested again in composite, not just composite optimization, I say just, which is actually almost mean. I mean composite optimization, but if you're interested in composite failure, for instance, today the teams were talking about building the next crash box on composites. They have been using a Duracell foam in the past, and now they want to become a little bit more innovative, and they are using now Radius, which is also part of the HyperWorks suite, to model the failure of a composite crash box. If you're interested in CFD, in the flow around your car, things like this, it's all available, it's all possible. What we need from your side is kind of indication, what are you interested in? And I think what we also can offer you, if you're interested in, we can set up additional webinars where we simply would focus on a certain topic. For instance, composite optimization, or CFD, or again Inspire. I mean, this was really just a very brief glimpse into Inspire. If you want to see more, yes, we are ready. So just let us know. And so, Greg, final word from your side, and then we're closing the webinar.
Yeah, no, I think we pretty much covered everything. Yes, like I said, just to reiterate, we want to help you guys. We want you guys to succeed. So yeah, feel free to get in touch. Okay. And I hope you enjoyed this. And thanks again to my Altair team, literally from around the world, for putting this together. So.